Hey everyone, and welcome back to The Foundry by Forge College. Today's explainer is called Applying Concepts to Industry Challenges, and honestly, get ready because we are officially moving out of the realm of theoretical physics and stepping right onto the factory floor of practical engineering. We're going to take all that high-level knowledge we've been building and figure out how to, actually use it in the real world.
But first, we've got to address the elephant in the room. Is a replicated ledger actually the right tool for your specific problem? Look, we've all heard the myth that blockchain fixes everything, right? But let's apply some pragmatism here. If you just need a database to keep track of your weekly grocery list, a globally distributed, Byzantine fault-tolerant replicated ledger is, well, it's literally overkill. I mean, a sticky note will do just fine. We need to know when it actually makes sense to bring in the heavy machinery.
Okay, let's dive into this. Here is our master schematic for today. We'll go from theory to reality, define 5 criteria for applicability, run some real-world industry tests, walk through the decision workflow, and finally, build your blueprint for success. All right, Section 1, from theory to reality, moving from synthesis to practical selection. So if you recall our previous lesson, Synthesis of Blockchain Fundamentals, you built this really fantastic mental model of the theoretical concepts, things like ledgers, consensus, and state propagation. But over here on the engineering reality side, we have to apply some very practical filters. This is where we transition from those abstract ideas to actionable selection. We have to ask the hard question: when do replication costs, data provenance, and transaction finality actually matter to a business? I want you to basically burn this quote into your memory. You should treat blockchain applicability as a structured decision problem, not as a checklist of buzzwords. Seriously, real engineers use strict filters, not fads, to decide if a distributed system makes sense. We don't just throw buzzwords at a whiteboard and, hope for funding. Moving on to Section 2, 5 criteria for applicability, the master schematic. Think of this section as the strict laboratory stress test that any idea absolutely must pass before it gets the green light for development. Here are the 5 explicit criteria you need to filter your ideas through. Number 1, tamper-evident data and provenance. 2, multi-party workflow with asymmetric trust. 3, shared state needs. 4, permissioning and access patterns. And 5, performance and latency tolerances. Now, these aren't just random checkpoints. They map directly back to that ledger and node mental model you've been building all along. Now, what's really interesting about this slide is how this scoring table translates vague gut feelings into concrete, measurable data. Just look at the breakdown here. We take a criterion, say data integrity. We measure the specific need for tamper evidence, and that tells us exactly why it matters. It determines if ledger primitives actually add unique value. It literally turns a maybe into a quantifiable yes or no. All right, Section 3, real-world industry tests, running the lab stress tests. Let's put this framework to the test in the real world. We're taking it completely out of the theoretical realm. For our first test, imagine a supply chain. You've got buyers, suppliers, logistics providers, auditors, and they all desperately need a verifiable chain of custody for goods, a situation where batch-level history absolutely cannot be altered. So they have a massive need for tamper-evident provenance, but among all these independent organizations, there's really only moderate trust. And here is how we'd engineer that solution. The requirement for high tamper evidence? That maps perfectly to using ledger hashes for shipment events. But what about keeping commercial details private? Well, we map that to off-chain storage for the full documents. This aligns flawlessly with the commit step in a transaction lifecycle, creating a totally immutable audit event for logistics providers without accidentally exposing their trade secrets. Pretty cool, right? Now, test number 2 brings us into the incredibly high-stakes world of interbank reconciliation. Picture multiple banks meeting to settle net obligations. The requirements here are intense. We're talking high correctness, low settlement risk, a massive need for a consistent shared state, and extremely tight performance constraints. So when you compare that need for high privacy and incredibly low latency against the available mechanisms, the choice becomes pretty clear. Intraday settlement windows require blazing speed, which means you have to use leader-based protocols, and that dictates your architecture, a permissioned ledger with a strictly limited set of validators. Not every institution gets to run a validator node in this scenario. Some will just run light clients to maintain that low latency. Our final test is clinical data sharing. Hospitals and research institutions need to share verifiable metadata about patient cohorts, but, and this is a huge but, They absolutely cannot expose sensitive personal health information, or PHI. So we've got extreme asymmetric trust here, paired with incredibly strict confidentiality requirements. And this brilliantly illustrates how we translate strict clinical rules into engineering realities. To protect that PHI, we keep the actual data off-chain and use selective disclosure. For data lineage, we anchor cryptographic hashes right on a permissioned ledger. The whole process of signing and attestation maps directly to capturing patient consent and safely depositing those datasets for research. Okay, section 4, the decision workflow, the assembly line for your capstone. As you explore more courses and programs at Forge College, you're going to need a reproducible mental model for your capstone projects. Think of this as an assembly line that takes 3 distinct inputs. Step 1, write a concise, measurable problem statement. Step 2, draw out the stakeholder trust topology. Step 3, collect hard performance targets. Explicitly mapping these 3 inputs forces you to confront the actual engineering limits of your idea, rather than just kind of hoping for the best. Let's define that second input a bit more clearly. A stakeholder trust topology is basically a visual map defining who runs validators, who operates observers, and who simply acts as clients. Now, why does this map matter so much? Well, because if you draw this out and realize that all your validators are internal to one single company, well, a distributed ledger adds almost 0 value compared to just a standard, auditable, centralized database. This workflow is designed to completely remove your bias. It forces you to base your decisions on objective, node role evidence rather than the subjective appeal of some blockchain silver bullet. If your use case scores high on provenance and the performance targets are feasible, awesome, you advance to architecture. But if the operational costs of the ledger outweigh the benefits, you reject it and use a central database. No hard feelings, just good engineering. Section 5, your blueprint for success. Key takeaways for the capstone. So the crucial point is that this blueprint bridges the massive gap between understanding abstract ledgers and actually solving complex industry problems. Keep these core takeaways in mind. 1. Provenance and tamper evidence are ledger-native values. 2. Your stakeholder topology will directly determine your operational cost. 3. Your performance limits will dictate your consensus choices. You absolutely must tie your capstone project justifications directly back to the transaction lifecycle artifacts you built. When you finish this process, there are exactly 3 outputs you need to bring to the next step of your journey. Just 3. Your scored rubric, your trust topology mapping, and your concrete performance targets. Which leads us to the ultimate question. Are you ready to take your prioritized use cases and engineer concrete solution architectures? Because that is exactly what we'll tackle in the next phase of this track. To continue your Web3 learning journey and dive deeper into designing these architectures, make sure to visit forge.college. Thanks so much for joining me on this explainer, and I'll see you next time.